The CISE logic is able to prove that a distributed program is safe, in the sense that it maintains some application invariant of interest. This demo presents the CISE tool written by Massa and Najafzadeh. The basic idea is in a paper by Balegas et al. Presented at Eurosys 2015. The logic is formalized and proved in a paper by Gottsman et al. To appear at POPL 2016. Let's consider a distributed system. Each horizontal line here represents a server or replica. Each replica carries a copy of the shared data or state, sigma. For instance, the data for a bank account is replicated at the bank's branches. State sigma must satisfy some property I, called the invariant. In the bank application, the invariant is that the account balance must be positive. Now let's consider some operation U. It consists of first reading state sigma at some origin replica, notation $U. This prepares the update to be applied at all replicas. This is a state transformation, which we call the effector, notation bang U. The effector is sent and eventually delivered, that is applied, to all replicas. In the bank example, consider the operation to compute interest. It would read the current balance, say 100 euros, compute the interest, say 5%, and generate an effector that will add 5 euros downstream. But when a concurrent operation V occurs, the effectors bang U and bang V may be delivered in any order. Here we have U and V, U followed by V at the top, and V followed by U at the bottom. Our analysis tool aims to verify whether all replicas will converge to the same state and whether the invariant remains true. Our tool works by checking the three following rules. Rule 1 is to check that the operation's preconditions are sufficient to maintain the invariant in any sequential execution. Rule 2 checks that replicas converge, that is, that the effectors commute. Rule 3 checks that every precondition is stable under concurrent updates. Gottsman and al. In the upcoming POPL paper show that if the rules are satisfied, then any execution satisfies the invariant. Note that checking the rules takes only polynomial time. Our first example will be a very simple bank account. The operations are a credit or deposit on debit by some amount. But today we'll ignore the operation that computes interest. The invariant is to maintain non-negative balance. This very simple example will show that the tool automatically uncovers inconsistencies and shows how to resolve them. We start with a very weak specification. Applying Rule 1 will show that debit needs a precondition, Rule 2 will show that debit and deposit commute, and Rule 3 will show that two concurrent debits can be unsafe, despite the precondition, and we will fix this issue, and finally the tool will show that the corrected program maintains the invariant. The first rule. It checks whether every operation in isolation maintains the invariant. If yes, the precondition is sufficient, and any sequential execution is correct. If not, this means that the operation's precondition is too weak. Now let's try out Rule 1 on the bank account example. Here we see a screenshot of our tool. The developer writes the properties of her program as Java annotations. On the top left, we see the invariant, balance greater or equal to 0, and underneath the specification of the two operations, deposit and debit. They both have the precondition that the amount that is deposited or debited must be positive. This is the specification for the effectors. Deposit adds the argument amount to the replica state, and similarly the effector for debit subtracts the amount. Now we will check the first rule by clicking on sequential test at the top right. As you can see, the tool finds no counterexample for deposit, so it's okay, but it does return a counterexample for debit, which shows that if the balance is initially 0, debit will make it negative. So let's fix the issue by adding a precondition. The amount being debited must be less than the current balance. Let's run the tool again. And with this correction, there is no counterexample. The program passes Rule 1. Now let's check rule 2. Do concurrent operations commute? If so, we know that the replicas will converge to the same state. Let's run the commutativity check. The tool will check all possible pairs. Does deposit commute with deposit? And to verify so, we have to check this assertion, and the assertion will be sent to the Z3 SMT solver, which tells us that it finds no counterexample. Same thing for deposit versus debit. No counterexample. Checking debit versus deposit, do they commute? No counterexample, they commute. Debit versus debit. No counterexample. Well, predictably, the check passes since we know that addition and subtraction commute, but here we have shown this automatically with the tool. Okay, now let's look at the third verification. We already know that operation U in isolation maintains the invariant, but what happens if some effector V bank concurrently changes the state? The insight here is that if U's precondition is still true after running V, then we know by the first rule that the effector of U will be okay and maintain the invariant. We say that the precondition of U is stable under concurrent V. Okay, return to the bank account example and use the tool. It will check for all possible couples, that is the precondition of deposit stable under concurrent debit? What about deposit under concurrent deposit? Is the precondition of debit stable under concurrent deposit or under concurrent debit? Now, in the interest of time, we will show only the latter two, which were emphasized in yellow. Now run the tool. Checking debit versus deposit, that is the precondition of debit stable under deposit? This is the effect of deposit. And there is no counterexample, good. Now check debit versus concurrent debit. Is the precondition of debit, which is here, stable under the concurrent effect, which is here? Send that to Z3. And Z3 comes back with a counterexample. If the balance was initially €1, two concurrent debits of €1 each, both together violate the invariant. The slide here now illustrates the counterexample. The balance was initially 1, precondition to debit of 1 is okay. However, concurrent debit of 1 makes the balance 0, and therefore the precondition of debit is not stable. If we continue, now the invariant is false. How can we fix the problem? Well, there are two possible alternatives. If you consider that freedom from synchronization is the most important consideration, well, the only alternative is to weaken the specification, for instance, to remove the invariant. Here we will assume that this invariant is important, and therefore the only alternative is the traditional approach, which is to add some concurrency control, avoiding concurrent debit with debit. Of course, this hurts availability and performance. Well, okay, we will add this concurrency control. We use the CISE's concurrency control abstraction, which is called a token. And we specify a token that disallows any debit to be concurrent with another debit. Okay, now we run the tool again to verify whether this actually solves the problem. And as you can see, the test now passes. So we have proved that the modified bank account is safe. That is, it maintains the invariant balance greater or equal to 0. Okay, now let's consider a more complex example, a file system. We consider operations to create, remove, move files and directories, and file updates. The invariant is that the directories form a tree. Now, to ensure this invariant in a sequential execution, we apply rule 1, and this shows that move may not move a directory under itself. So we add the corresponding precondition. Rule 2 concludes that concurrent writes to a same file do not commute. We can fix this issue without violating availability by decreeing that a file is a CRDT. In the interest of time, we will focus on rule 3 now, and we'll go back to the verification tool, which will show that the above precondition of move is not stable under concurrent move. Here's a partial view of the file system specification. We want to find out whether the precondition of move is stable versus a concurrent move. We run the tool. And you can see, so we are checking whether move directory is, its precondition is stable under a concurrent move directory. As you can see, the assertions that are given to Z3 are quite complex, but Z3 now comes back with the counterexample. The precondition is not stable. So here we illustrate the counterexample that the tool has given us. So consider we have 3 directories, the root, /A, and /B. The top replica asks to move /A under /B. The precondition, which was imposed by rule 1, is that /A is not under /B, which is true, so we're okay. We have a new state illustrated here. Now, concurrently, some other replica asks to move /B under /A. Once this happens, the precondition is not true anymore. That is, it is not true anymore that there is no path from B to A. And indeed, if we were to continue and apply the first move, we come to this new state where A and B form a cycle which is disconnected from the root, and obviously this is not a tree and it violates the invariant. How to fix this? Again, if availability is essential, one approach is to weaken the specification. For instance, Microsoft OneDrive will lose A and B and all their descendants. Other file systems, such as Google Drive or GeoFS, exhibit other anomalies. Here, we will consider that the invariant is important, and we decide to fix it by adding some concurrency control. Okay, let's add some tokens. Interestingly, we don't need to disallow all concurrent moves, only the ones that make one a descendant of the other and vice versa, as in the counterexample. So now we will check rule 3 again. So we're checking stability of move directory versus move directory. And you can see this is the specification of the tokens. You can see it is rather complex. It does not disallow all concurrent moves. And thanks to this token now, there is no counterexample. The modified file system has been proven safe. Okay, demo is over. Our goal was to design a distributed system that is both available and safe. Synchronization is undesirable, but it is sometimes required in order to maintain the application invariant. This demo showed how to use the CISE logic to identify exactly where concurrency is problematic. And the developer can choose to fix the problem either by weakening the specification or by adding synchronization. The result is proved correct and has just the minimal amount of synchronization that is strictly required for safety and no more.